So we take fourth sem module 5. The one thing is remaining in your syllabus is some theorem on tree. All the remaining will discuss in the lecture in your class. So here we want to discuss some theorem on tree. Before we start some theorem on tree, because it's too much gap between the last class of graph theory and this class. So first we remember the definition of tree. A simple connected graph has no cycle is called a tree. According to this definition, we construct some theorem which is very important for your examination, as well as if you gather some concept from this, you can easily utilize to solve some multiple choice question that should come in the next week as a practice set. So we start the first theorem. A graph G is a tree if and only if there is one and only one. Here we mistake one, so that should be one here. This one is one. Okay, one and only one. Okay, one and only one path between any two vertices. মানে দুটো ভার্টেক্সের ভেতরে যদি একটা এবং একটাই মাত্র পাথ থাকে তাহলে সেই গ্রাফটাকে ঝিপ। ইটস এ নেসেসারি অ্যান্ড সাফিসিয়েন্ট কন্ডিশন। তার মানে যদি দুটো ভার্টেক্সের ভেতরে একটা কানেক্টেড গ্রাফে একটাই পাথ থাকে যে কোনো দুটো ভার্টেক্সের ভেতরে, তাহলে ট্রি হবে। আর ট্রি হলে যে কোনো দুটো ভার্টেক্সের ভেতরে দুটো একটাই মাত্র পাথ থাকবে। সো উই স্টার্ট আওয়ার প্রুফ। দ্য নেসেসারি কন্ডিশন. Suppose G is a tree. First we consider G is a tree, and then G must be connected, and hence there must exist at least one path between every pair of vertices. Because we have considered G is a tree, first we consider G is a tree, next we used to prove that there must exist only one path between any two vertices. So here we consider that G is a tree. Since G is a tree, there must be a only one and only one path. Only one path. Just we consider there is a path, at least one path between every pair of vertices. Otherwise, it should not be a connected graph. Suppose that, it's very important. Suppose that between two vertices Vi and Vj of the graph G, there are two distinct paths. Okay, here we use the contradiction method. What is the meaning of contradiction? Which you want to prove? We just supposing the opposite to the result. If it is happen that our assumption is wrong, then we say that our assumption is wrong and the statement is true. এটা আমরা নেগেশন মেথডে প্রমাণ করব। যেটাকে প্রমাণ করতে চাইবো তার অপোজিটটাকে আমি কনসিডার করে নেব বা ধরে নেব। ধরে নেওয়ার পরে দেখব যে আমি যা ধরেছি তা ভুল, সুতরাং যা দেওয়া আছে তা ঠিক। ওকে, সো দ্য ইউনিয়ন অফ দিস টু পাথ উইল কন্টেন এ সার্কিট. Because here we consider the two vertex, any two vertex. If we consider Vi and Vj be two vertex such that there is more than one path. If there is more than one path, according to this graph, you can easily observe that if Vi and its Vj, there is a path, there is another path. If it is happen, then they must have a circuit. They must form a circuit or a cycle. If it form a cycle, then it should not be a tree. So our assumption is wrong. This is our assumption which should be wrong. Then we can say that if the graph is a tree, then any two vertex should not have more than one path. If there is more than one path, it forms a circuit which contradict that our graph is a tree. Okay, next we move to the next sufficient condition part. Suppose, what should be the sufficient condition? The sufficient suppose first we consider the graph. Any two vertex must have a path. You have to prove that this graph should be a connected graph. This graph should be a tree. That is our motto. Suppose that there is one and only one path between every pair of vertices of a graph G. আমি কনসিডার করলাম জি একটা গ্রাফ যার যে কোনো দুটো ভার্টেক্সের ভেতরে স্টিল উই আর নট কনসিডারিং জি ইজ এ ট্রি ইউ হ্যাভ টু প্রুভ দ্যাট জি ইজ এ ট্রি বাট সাপোজ উই কনসিডার here we consider any two vertex must have a path that represent that the graph is a connected graph. Now existence of a path between every pair of vertices, we have already mentioned that, assume that G is a connected graph. Since it's a connected graph, a circuit in a graph having two or more vertices implies that there is at least one pair of vertices Vi and Vj such that there are two distinct paths. Here we consider any two vertex only one path. That is very important line for you. Mention this line. If the graph is connected but still it's not a tree, that means it must have a circuit. If it has a circuit, it's represent that any two vertex, at least any two of them of all the vertices must have more than one path, which contradict our assumption that we just consider there is an only one path. Since G has one and only one path, this is very important, one and only one path, so it should not be happen there forms a circuit. So it's a simple graph, connected graph, satisfy the definition of tree, so it should be a tree. Okay, next we move to the next theorem. Second theorem. A tree with n vertices has n minus 1 edge. একটা ট্রিতে যদি n খানা ভার্টেক্স থাকে তাহলে n minus 1 খানা এজ থাকবে। We shall prove by mathematical induction method. That means the first step is the basic step, second step is the inductive hypothesis, and the last step is the inductive step. We have already learned this step in your lecture. It is easy to write that if the graph has only two vertex, only one vertex, then the number of edges should be 0, which satisfy n minus 1. So this one is your diagram. This represent if a graph has two vertex and it's a tree, the number of vertex is 2, therefore the number of edges should be 1, and it satisfies n minus 1 because n is the number of vertex. If we consider the tree has 3 vertex, then the number of vertex here represented by 3, and number of edges should be 1 into 1 plus 1 2, so you should write in 3 minus 1 2, that is n minus of 1. That means the basic steps satisfy the theorem. Inductive hypothesis assume that the theorem is hold for all trees with fewer than m vertices. Fewer than m vertices. We just consider result is true for n equals to m. It's very important step. Here we write everything because I am not in the class, so I am trying to write everything in your note, which will already provide to your forum. So you have to clear everything in this note. Here we consider this one, the number of vertices. Here we consider the tree is broken at there, but just let us consider a tree with m vertices and let T, E, K, B and H with the n vertices of Vi and Vj shown in the figure just here. And T is a tree, there is no other path between Vi and Vj because it's a tree, they should not have more than one path, so V1 to Vj has exactly one path. How we do? What to do next? Just delete the edge EK. Okay, just to delete the edge EK, that means it's become two component. Here we write this concept, we delete this, which we should found the two component. Here we write this concept, here we write this concept, skipping the remaining part of the theorem T1 due to have, and we should consider every of the component because they are two these two should be the connected graph because it's a component. There is a two component. You can easily observe that the number of vertices should be less than m. If we consider in the first component, here we mark it as T1. Here T1 consists exactly p number of vertices and T2 consists exactly m minus of p number of vertices, because here we consider the graph as m number of vertices. So the total number of vertices, p number of edges and m minus p number of vertices and m minus p number of vertices. Therefore, according to the theorem, it says that in the component T1 the number of edges should be p minus 1 because it's and the number of vertices minus of 1. Just we assume this, the result is true for n equals to m. If we divide this graph in the two partition in such a way that every vertex should consist less than m number of vertices, therefore it should satisfy and the norms of this. So in the first component, the number of vertices should be p minus 1. In the second component, the number of vertices should be m minus p minus 1 because we have already considered m minus p number of vertices. So if we add this to one, that's represent the total number of vertices in the first component plus second component, that is m minus 2, and we just delete a edge ek. That means the total number of edge should be m minus 2 plus of 1 m minus 1, which prove that if the graph has m number of vertices, they are exactly m minus 1 number of edge. That is the inductive step, and since it's an inductive step, it's proved that the result is true for any positive integer, because from the basic step we have already proved for the value of 1 2 3. That means if we consider m equals to 3 from inductive step, the result is 2 for 3 plus 1 4. If we consider the result is 2 for 4, therefore the inductive step says 4 plus 1, it's 2 for 4 plus 1 5, and so on. So this is your second theorem. In the next lecture, we move to the third theorem of tree.